mass class. Now, I could compare the 720. Let me just scroll this down a little bit. See if I can get on the screen. I guess I can't. That's a drop of 764 down to 720. That's a drop of, let's see. If I look at fit statistics, global test, that's a drop of 43 points. Well, remember if I looked at the previous model, which had BMI as a continuous variable, it dropped by 52 points. The previous model had a bigger drop because the previous model had a minus 2 log L of 712, and that's smaller than the 720 that I have for minus 2 log L for this model. And all things being equal, smaller is better. But I also said beware, the bigger models will always be smaller than less big models because the minus 2 log L will always drop. It might stay the same, but it'll never get bigger as you add more and more factors to the model. So maybe a better metric to decide whether this model is better than the previous model. This model, which assumes a step function relationship with body mass index, is any better from the previous model, which assumed a linear relationship, is not to compare the minus 2 log L, but to compare the AIC statistics. Here it's 728, 8 points higher, because now what we had to do is include a B0 term for the intercept, a B1 term for the coefficient of Ohana, and two other terms, a B2 and a B3, for the two indicator variables for the three categories of body mass index. In the previous model, the value for the minus 2 log L was 718, which is smaller than the 728. And again, smaller is better. So this is suggesting that of these two models, the model that makes the assumption of a linear conditional relationship between body mass index and your log odds of disease is actually fitting the data set better than the model that assumes that your risk changes with categories but stays same within categories. In other words, the more recent model we've been looking at is the step function model. Doesn't seem to fit as well. So based on that, I might prefer to go back to the previous model, the model that assumed a linear relationship conditioning on the intervention variable to describe the relationship between body mass index as a continuous variable in your log odds of disease. But before I leave this, let's look at the rest of the model. Let's look at the parameter estimates. Here's our model with a intercept term, a coefficient of the Ohana variable, and two other terms. BMI class 3 is the indicator variable for being overweight. BMI class 4 is the indicator variable for being obese. Those are the variables that SAS created for us. A BMI class 3 variable, 1 if you are overweight, 0 otherwise. Another one, BMI class 4, is a 1 if you're obese, 0 otherwise. We're mainly interested in the coefficient of the Ohana variable. The coefficient is minus 1.03. That corresponds to an odds ratio of 0.35, very similar to the 0.33 we had before. Meaning regardless of how I control for body mass index, as a continuous term assuming a linear relationship or as a categorical variable assuming a step function relationship, the odds ratio measuring the effect of Ohana with the outcome is still around 0.33. It's 0.35. It's changed slightly. It's still statistically significant. P is 0.0001 for that test. But if I was going to report either of these two models and I wanted my decision to be based partly on prior knowledge and partly on the fit of the data, the previous model, the model with the continuous BMI variable, assuming a linear relationship, seems to fit better than this categorical variable relationship. And that's how you might decide which model you might present as your final model in an analysis, by comparing the relative fits of candidate models. So I haven't talked about the bottom part of this output yet, so let me talk about that in the last model I'll look at. So now let me go back and rerun the model which I showed you at the end of class last Monday. Let's fit a model not only controlling for BMI, but controlling for age, hypertension, whether you're on hypertension medications or not, diabetes, BMI. So let's see, we're assuming here a continuous linear relationship for BMI, another one continuous relationship linear for the two blood pressure variables. So we're making assumptions here about the relationship of continuous potential confounders to our outcome. We're making the assumptions of linear relationships. We're also controlling for categorical variables like CVD and marital status and sex by this. Let's see what we get here from this model. This is where we'll end up talking about SAS today. This is the model we looked at the end of class, on end of session last week. Let me go back to the beginning of this printout. It looks exactly the same. 172 deaths, 500 people who didn't die. Again, the intercept-only model has a value for the intercept of minus 2 log L of 764 points. Now if I look at all the covariates, it's dropped from 764 down to 609. It's dropped 155 points. But that came at the cost of including 11 different risk factors in the model. And that's why there's 11 degrees of freedom associated with this. But that's still a significant drop, saying the model with the covariates is a highly significant different model than the model with the intercept only. So the global null hypothesis that says all the risk factors have zero coefficients. In other words, only it's the intercept that's the only thing that matters. Everybody has the same risk. The global null hypothesis is not supported by these data. The problem is we don't know why we're getting this small p-value for this test of the global null hypothesis. It could well be that each individual risk factor is important. Or it could be that only one of them is important. And we don't know which one it is. And more importantly, we're doing this analysis with one main goal in mind. We want to know whether the Ohana variable is important. And this global null hypothesis is not helping us. What we need is to look at the fitted model. So that's what I'll do now. Here's your fitted model. Here's your coefficient of the Ohana variable, the log odds ratio. It's still statistically significant. P-value 0.002, meaning controlling for age, blood pressure medications, diabetes, body mass index, sex, cholesterol, blood pressure, cardiovascular disease, marital status. The people who received the lifestyle intervention have a significantly different risk of dying than the people who didn't. With a log odds ratio of minus 0.67, we can turn that into an odds ratio. E to the minus 0.6715 gives us an odds ratio of 0.51, meaning controlling for all these confounding factors, people who received a lifestyle intervention, their odds of dying is roughly half of that of the people who didn't. It's no longer 0.3 or 0.33 or 0.36 as the crude analysis, the crude 2x2 table. There is confounding here, but after controlling for all those confounding factors, we get an adjusted odds ratio of 0.5 as our best guess of the true causal relationship, the strength of that dotted line on that causal diagram that we looked at before. So this is how we control for many potential confounders, by building models that, in this case, control for each individual potential confounder. And as an aside, let me just point out two other things with this printout. We can also look at each of the individual potential confounders to see which ones are significant risk factors. So we see, for example, that marital status is a significant risk factor here. The odds, with an odds ratio of roughly about 0.6. In these data, married people had an odds of dying which is 0.6 that of non-married people. So it looked like it's a protective effect. Age had a p-value of 0.05, borderline significant. For every 1 year increase in age, your odds of dying increased by a factor of 1.02. That's the effect of age in this model. So not only do we get an effect of our risk factor of interest, Ohana, we also get estimates of all the risk of the effects of all those other risk factors in the model. So it gives us information about other things too, but we're mainly looking at the effect of the Ohana variable. One last thing to say about this model before we leave it. The piece I didn't leave to you is, let's look at this very last number, this C statistic. In SAS, the C statistic is something, it's called by other people the area under an ROC curve. What do I mean by that? It's another measure of how well this model is working. And what it does is the following. Let's imagine we take this fitted model, and one by one we take each person in our data set, plug in his value or her value for Ohana, age, hypertension medications, diabetes, plug them into this model, multiply them by their coefficients, add them all up, we'll get that person's predicted log odds of dying. We could turn that into an odds of dying by getting rid of the log, taking e to that number. We could turn that odds into a risk. So what we can do is get a